Okay, welcome back. Here are a few examples of problems that are like the ones you might see in the problem set from section 10.4. That would help. And there are many others. Again, study the text. Email me if you have questions on any of these that you're struggling with. You'll also, I think, see that we can maybe solve these problems a little bit differently than using vectors. But I do want to show you this nice way using vectors. So here we go. First of all, here we have two vectors. Now, before I get into this, remember the I and the j I talked about being unit vectors. I said I'd mention them a little bit more. And the way we look at that is the following. I is basically the vector 1, 0. So it has a length of 1. That's why it's called a unit vector in the x direction. J is the vector 0, 1. So when we see a vector being described as 2i plus 3j, the other way to think about it is simply 2, 3. Not meant to be confusing, but sometimes can be because we have so many different ways of talking about vectors. This is very common in this text and in this course. This is also very common. You might prefer this because it's just less cumbersome. Another way to think of this one would be 3, negative 4. And in our last short video, we talked about a position vector. We could refer to these simply as position vectors. So basically, I want to put these two together. In the last video, we looked at the geometric way of just putting these two together, and that would be just plotting 2, 3 as a vector, and on the end of it, plotting 3, negative 4, moving that direction and seeing what you end up with as a result. But in this case, we're going to do it analytically because it does have a benefit. So if I wanted to find w plus v, I'm basically adding the corresponding components. So I'm going to have 5i, add those two together, minus j. And that's what you would find, of course, if you just looked at them in terms of this other notation also. If we wanted to subtract them, we're just going to subtract the coordinates. So it's negative I. That minus that is going to be 7j. And then finally, if you want to double v and add it to 3 times w, you might guess that you're going to twice that is going to be 4. 3 of that is 9. So we get 13i. We take twice that, would be a 6. 3 times that is negative 12. So we should get a negative 6w. Sorry, 6j. So unit vector notation would give these answers. If we wanted to continue with this notation, we could definitely do that. So this is how we can add, subtract, multiply, even work with what we call a scalar multiple for a vector in order to get these results. This next one tends to be, it's a very unique type of a problem. For some reason it causes issues, but it doesn't have to. There's a nice formula for this in the text, but I tend to not go with that formula. I just try to reason this out. We want to find a unit vector, which means it has a length of 1, or maybe not a length, but a magnitude of 1. Magnitude equals 1, but in this direction. So what it really comes down to is this. If I would plot the vector 4j plus 3i, it's pretty much what you think. You move over 4, you go up 3, and that's going to be my vector. Now, we know the length of that vector. Its magnitude is 5. 3, 4, 5 right triangle. So I pick some nice numbers. Okay? If I want a unit vector, but in that direction, all I have to do then is to cut this into 5 equal parts. So maybe that's 1/5 of it. So that little purple part is now going to be the same direction as this one, but it's only of length 1. So if you think about how did I come up with that, well, I just have to take these components, the 4 and the 3, and I'll call this new vector u, that would be u, is going to be 4/5 I plus 3/5 j. I noticed I should have made that I. I don't know why I had it as j. So this is now a unit vector, but it's in the same direction as the original. And you can check both of these. You could find out what the angle is, and you could also find out how long this one is by finding the magnitude, and you would find it to be 1. Final example, and there are many others that you want to study in this text, but this one should bring us back to when we were working with law of sines, law of cosines. But we're going to tackle it from a little bit different direction. Plane travels 500 miles per hour due south. There is a wind of 800 miles per hour northeast. Find the velocity of the plane relative to the ground and find the direction of the plane. So let me start by getting the picture. If I want to think of a 500 miles an hour due south, this is where our vector comes into play. I'm going to represent that as 500. It's not its length, it's the quantity. But it is going due south because, of course, I'm going to deal with this and consider that to be south. This is north and so forth. The wind is going 80 miles per hour northeast. Now, we can kind of deal with this a couple different ways. I could put the 80 miles an hour northeast, which would be here at a 45-degree angle, because that's what northeast means. Or I could put it here. It really doesn't matter. A lot of people like the tip-to-tail method, so I'm going to put it here. So I'm going to think of this as I'll make it a little bit bigger than it should be, just so I have a better picture. There's 80. All right? So basically, the plane is facing south, going 500 miles an hour, but it's being blown back a little, but it's still faster than the wind, so it's able to plow through the wind, but it is being pushed this way and back, so it's going a little bit slower, not quite a straight headwind. So what's really happening is the plane is really going in this direction. Even though it's kind of facing, here's my little plane, it's facing that direction, it's actually traveling this direction. So once we get this picture, we should be pretty good. Now, a couple things about it. We know this is 45 degrees. Okay, so I basically want to find the magnitude of that orange. Now, of course, one way to do it is to use the law of cosines, and quite honestly, that is not a bad way to go about it. But what I'm going to do is this. I'm going to come up with a vector for the plane. Vector for the plane is basically going to be 500 j. And I might even make that negative 500 because it's going down. All right? Because I kind of consider this to be my normal xy axis right here. All right? And then I want a vector for the velocity of the wind. Well, the velocity of the wind, if I use components, is basically going to be kind of these values. That would be my I and j component. This would be my I, this would be my j. Well, both of them are going to be 40 radical 2 because we know that if we take this and divide by radical 2, 80 divided by radical 2 would be 40 radical 2. So it would be 40 radical 2 I plus 40 radical 2 j. And so now what's neat about this is the velocity of the actual plane, or the end result, I'm going to call it of the resultant, is going to be basically just the sum of these two. So we've got 40 radical 2i plus, you add these two together, you're going to get 40 radical 2 minus 500 j. So that's the vector represented by that orange, this orange kind of ray. And then now if I want the velocity of the plane, I just have to find its magnitude. The magnitude of that resultant is going to be, and I'll let you finish this, square root of this squared plus that squared. That's just the Pythagorean theorem. That's all it is. Because I basically have already found these two values. And then the direction of the plane, you basically have to find one of these angles. It's going to be an arctangent. So the direction would be the arctangent of, if I think of this one right here, I call that theta, of, let's say it's equal to theta. It's going to be this value, okay, and that was the j over this value. Clean that up a little bit. Now, I don't want to make you think that there's no way you can use the cosine rule, sine rule, or any of those other rules that we've had. But I did want to kind of open your mind to being able to use vectors when it can be appropriate. If I would give you something like this on the test, I don't care how you want to get that magnitude. You might even want to go ahead and do these calculations, but also do the calculations with the 80, the 500, and the 45, and see if the cosine rule gives you the same value. It should. If not, we did something wrong. So, the basics of vectors so far is to be able to add, subtract, multiply vectors. Not so much multiply vectors, but multiply them by a scalar. Deal with unit vectors. And there'll be a variety of problems that you have to kind of set up a situation. But once you set up a situation, you should be able to see a triangle with part of the vectors that are given and then the resultant in some way. And you're going to be asked questions about the magnitude of that resultant vector and possibly the direction. So good luck with the problem set from 10.4. As always, if you have any questions, please let me know and I'll get back to you as soon as I can. We will talk more about vectors on Monday. Thank you.